Hi, my name is P3, working at Hyundai Motor Company. In this talk, I'm going to introduce Guider, Unified Runtime Performance Analyzer, and explain how to trace Linux system using it. This is a summary for my talk. First, talking about diverse performance tools and problems and Python. Next, introducing Guider and its useful features and explaining how to trace our Linux system. Finally, showing demo how to use Guider. To analyze performance, logging and using tools are most effective ways. Logging is very useful for recording specific information, but understanding log requires domain-specific knowledge, so system-level engineers or new members are difficult to understand them usually. In addition, adding new logs requires source code and toolchain for rebuild. It's very boring and time-consuming. It's also difficult to record and analyze too many logs because of the limitation for memory and time. So we prefer to use performance tools. It's very comfortable and effective to analyze performance at system level. Some nice tools doesn't even require rebuilding target program, installing itself with dependent packages, restarting target task. But sometimes too many tools confuse us. Determining the right tool from a variety of performance issues is not easy. Moreover, the results of a single tool are not enough. So it is common to use multiple tools to summarize, reprocess, and analyze the result. However, not all tools are easy to install and use, since there are many requirements such as kernel, configuration, package, build, and re-execution. The older the system, the more difficult it is to use. The same goes for visualization. So I decided to make a new performance tools that can analyze all performance factors easily. But there were immediate difficulties and I ended up choosing Python. Finally, for the following reasons, there were many things to be implemented, but Python has productive expressions and data types. It's difficult to learn how to learn new language, but Python is very easy to use for beginners. There are needs for many packages, but Python has many useful built-in packages and powerful visualization packages. Yeah, it's very interesting. There are needs for performance and compatibility, but Python provides attractive binding features to C, C++ libraries. I don't need to implement all, just link some things in standard libraries by using C types, similar to DLOpen. Guider never use external binaries, such like executable programs, non-standard libraries, Python packages, except for matplotlib for some kind of visualization features. Most of Guider features are implemented directly using standard libraries, such like LPC. That's the reason why Guider doesn't require any rebuild, install, configuration. In addition, it can be applied with only 1 megabyte of storage space. These characteristics are very attractive in embedded systems, especially. All features of Guider are supported in Linux and Android, and it also provides some limited features on macOS and Windows. So from now, let me introduce some current features of Guider. First one is monitoring system resources in real time. This feature works by periodically updating stats for system resources and events. Some resource is about CPU, memory, swap, block, network, storage. As shown in the picture, in the first part, system resource information is shown on the top line, such as the number of cores, RAM, swap. And additional system information such as context switching, interrupt, running task, memory zone, and performance stats using PMU are also displayed. In the second part, important system-level resources and events are printed. System stats such as CPU usage, available memory, swap usage, memory reclaim, block I/O, network I/O are most precious information for performance analysis. In addition, core usages are also printed. Although not shown in the picture, governor, clock, temperature for each core can be shown together using specific options. In the third part, storage information about busy, workload, available space is shown for each device. Heavy storage workload can cause serious performance degradation. That's the reason why we track those stats. In the upper part of the picture, network information about inbound and outbound is shown for each device. In the lower part of the picture, not only system resources, but also task resources are shown with their attributes in real time. It's a little bit similar to Linux top command. Usages for CPU, virtual, physical, shared memory, swap, block I/O, and net memory details are printed well. The shown tasks are sorted by CPU usage by default, but you can change the sort order using a specific option. The task filter is also available to show only specific tasks. All or specific function calls can be monitored for specific tasks in real time. In addition, stats about function calls are also printed, such as average, minimum, maximum time. At this picture, all function calls are shown with backtrace. That usage is not about CPU. It's the proportion for the total function calls. So this feature is useful when finding frequent calls or measuring specific function call count, including backtrace. Of course, there is another function monitoring feature to measure CPU-intensive calls by sampling techniques. The task filter and function filter are also supported. All these calls, including backtrace, can be also monitored for a specific task in real time. In addition, syscall stats are also shown, such as elapsed time, error return together. This feature is very useful when finding syscalls that take a long time, measuring specific syscall count, checking syscall error returns, The task filter and syscall filter are also supported. All open files, sockets, pipes can be monitored for each process in real time. Files are printed with position and open flags. TCP and UDP sockets are printed with binding and connection status. Unix domain sockets are also printed with the file path. This kind of information is very precious when debugging issues or performance tracing. The process filter and the file filter are also available. By using the file filter, monitoring all processes that open the specific files or binded specific sockets is possible. Previous monitoring features are for tracking current status, but if someone wants to see a summary of system changes for a long time, the profiling features can be good solutions. As shown in the picture in the top table, changes for system resources and events are also printed for each interval. CPU usage, available memory, block I/O, swap usage, memory reclaim size, running task, network usage are summarized in each line for each interval. Because of screen length limitation, some fields were truncated. In the middle table, changes for storage usage are displayed with total summary. There was no storage operation in the profiling time. Busy, workload size, available space are summarized for each time interval for each device. In the bottom table, changes for network usage are printed with total summary in the red box. Workload for inbound and outbound is summarized for each time interval for each device. Next, profiling features for tasks. In the first table, changes for per process CPU usage are also shown with task attributes and total summary for each interval. Total summary information in the red box represents CPU usages such as minimum, average, maximum, and total for each task and whole system. In the second table, changes for per process virtual memory usage are printed with task attributes and total summary for each interval. The overall format is similar to the CPU table above. Although not shown in this picture, various types of tables are reported together, such like scheduling delay, physical memory, block I/O, C-group usage. By using these features, measuring and comparing resource usages are possible for many test cases. Text-based analysis is specific but less readable. That's why Guider provides visualization features in SVG format. Using the SVG format output in your web browser, it provides an easy-to-view and responsive interface. First visualization feature is about resource graph. As shown in the picture, the top box shows graphs of CPU usage for running processes. The box on the right side is the label list for those CPU graphs. And middle box shows graphs of block and network I/O for the whole system. The bottom box shows graphs of memory for the whole system. Of course, process graphs about block Network memory sources are also available. In addition, filter option for all of them is supported. As you can see, this visualization feature makes it easy to understand big data collected for a long time. And it also helps to understand trends in resource usage. This is also good for communication with other people. Next visualization feature is about scheduling. The scheduling data is very large and very difficult to analyze one by one. Therefore, as shown in the picture, scheduling data such as time slice, preemption, and blocking should be visualized prior to the detailed analysis. Using the SVG format output in your web browser, you can view details for time slices. It's very effective for analyzing multi-threaded programs, interactive services, delayed tasks, core utilization. In addition, this feature also allows for scheduling events as well as other custom events having timestamps for start and end. It's some kind of simple corner chart in SVG format. Last visualization feature is about call stacks. Analyzing only last called functions without whole backtrace is difficult because standard functions such like read, write can be called by any other functions. Above all, in most cases, last called functions will not cause all the problems. The problem is likely some other functions that called those last functions. Therefore, to analyze performance problems in function level, we need to be able to see the whole including each backtrace. In this case, this frame graph feature is very useful to analyze call stack-based profiling result for CPU usage, blocking status, memory leak, syscall trigger, function call. As shown in the picture, last functions at the bottom of each call stack are various. So we need to analyze upper functions that contains them. I guess modifying those functions will improve your application or service performance actually. Opening the SVG format output in your web browser, highlighting, zooming, searching specific functions or call stacks are also available using mouse and keyboard. Okay, so far I have introduced some useful features of Guider. So from now on, I would like to explain tracing features. Because of time limitation, I'm going to explain only function tracing, signal tracing, syscall tracing, I/O tracing. The target of function tracing is divided into three kinds of things. First, native calls such as C, Rust, and Go. Second, zip-compiled function calls such as Java, Node.js. Last, Python calls using interpreter. Syscall tracing is about just system calls, and signal tracing is about signals delivered to the target. And finally, I/O tracing is about I/O operations at various levels, such like device, task, file. So tracing target is divided into program and task. Program is just a binary not yet executed from storage. So Guider can execute the target program at which point the tracing begins. from loader. Task is a running thread, so guider does not require restart of the running task for tracing. Instead, it attaches to the target thread directly. Tracing commands are various. If you want to see detailed commands and options, please refer to guider help. The first tracing feature is for native functions such as C, C++, Rust, and Go. Native function tracing is started by btrace command. The command is implemented using breakpoint called trap. Breakpoints for all symbol addresses from ELF and dwarf sections are injected to the target task's virtual memory by guider itself, so guider can detect events for function call and return from the target task by ptrace. Guider can even read and manipulate registers and memory for the target task when function events occur. As shown in the picture, call stacks are shown with various depths for Go program in real time. Arguments and binary name for each function are also printed together in a line. The G option in command line is task filter. That means all tasks have a name including Go will be targets for function tracing. The H option means printing backtraces. If there was no H option in the command line, just all function calls are printed without depth indent. Function filter is also available with the C option to trace only specific functions. The C option supports specific characters such like asterisk for inclusion or subcomplex for exclusion. Using the H option, all backtraces are also printed every function call. As I already mentioned, guider can read and manipulate registers and memory for the target task at the time of each event. In addition, various features such like task control, injection for Python code, and external binary, remote call are also available using call command. As shown in the picture on the right side, many call commands are supported to handle specific function call events. Let me explain some call commands. First one is execute. It executes external command when function called. Next one is filter. Print context if only specific conditions are met. Get arg. Print specific argument value. Set arg. Manipulate specific argument value. Get return. Printing return value and elapsed time when function returned. PY file. Execute specific Python script remotely. Read mem. Print specific memory value. And write mem. Manipulate specific memory value. Next one is sleep. Wait for specific seconds. Syscall. Call specific syscall remotely. And last one is user call. Call specific user level call remotely. This kind of call commands are very useful when analyzing more deeply. This is about how to use call commands. Call commands are appended to the function filter with vertical bar in the C option. The command line at the picture means first, start tracing only write function from yes program. As you know, yes is just a Linux command that print arguments value infinitely. So yes program will print ABCD string repeatedly. And the print function is implemented inside yes program using the write function in LPC. Next, when the write function is called, print the memory value pointed to the first argument with backtrace. Argument value starts from 0th in guider. Therefore, a function argument for the write function is specific memory address that points to the value ABCD to be written. I guess the yes program is implemented using buffered write because multiple ABCD strings are written at once by the write call. The previous function tracing features for the native functions, but how about programs written by JIT-compiled languages such like Java, JavaScript? It's impossible to get symbol mapping information about them using only ELF tables, but if the target task provides guider with JIT-compiled symbol address mapping information, and JIT-compiled function calls follow procedure call convention, it's possible to trace them. Java and Node.js can export symbol address mapping table using external file at runtime. Then guider can trace their JIT-compiled function calls after importing the mapping table. Like this. This is a tracing example for Node.js. As shown in the picture, there are JIT symbols in red boxes and native symbols. These tracing features also support function filtering for JIT symbols. Next tracing feature is about Python function. Python function tracing is started by pytrace command. The command will print all Python method calls. As shown in the picture, Python call stacks are printed in real time at various depths that, depending on the stack frame, file path, and line number for each function are also printed together. The target was IO top program that's written in Python and prints IO usage every second in real time. Call commands used in previous native function tracing are also available for this feature. Next tracing feature is for syscall. Syscall tracing is started by strace command similar to original Linux command. The command will print all syscalls and their arguments converted into an easy-to-understand format. As shown in the picture, syscalls are printed with backtrace, return value, elapsed time in real time. Call commands used in previous native function tracing are also available for this feature. And syscalls can be printed with backtrace, including JIT-compiled symbols like this. JIT symbols are shown in the red boxes. Using this feature, it's easy to analyze how long syscalls are taking and which JIT-compiled function call those syscalls. As shown in the picture, with the specific options such as Q and PY stack value, Python stacks related to each syscall are printed. This feature is very useful when analyzing specific Python server programs for tuning. For example, there is a low throughput server program written in Python, and if I'm going to improve performance of it, first of all, I can check the size arguments for each syscall, such like receive and send, and increasing them if they are not enough. And finally, verifying results for bigger bandwidth. During this process, if I cannot understand the server program deeply, including code, it would be very difficult to change it. But if I already know which point should be changed, such like Python function calling network syscalls, this feature is good at these cases. Next tracing feature is for signal. Signal tracing is started by a sigtrace command. The command will print all received signals for the target task. In addition, the cause of the signal generation and the sender can be also printed when receiving segmentation fault child signals. As shown in the picture, received signals are printed for target threads in real time, and those threads were terminated because of segmentation fault caused by wrong memory access. Backtrace option and signal filter option are also available for this feature. Using backtrace, you can analyze which function is being executed when the target task receives signals. This feature is useful when monitoring multiple threads to analyze abnormal termination, such as segmentation fault. Last tracing feature in this talk is for I/O. I/O tracing means analyzing which task performed which operations on which files, on which devices, and at what size. And it's not only for specific tasks, but also all tasks, whole system. So it must be possible to correct all system I/O events, including various metadata such like task, device, inode, workload information. The I/O tracing consists of these steps, 3 steps. First, recording all system I/O events. Second, processing recorded data, including conversion. Last, summarizing and reporting result. In the command line, IOREC command is for recording system I/O events into a specific file. Report command is for processing data and reporting to specific output file. As shown in the picture, first report information is about task workload. In the red box on the right side of the picture, block workloads are shown with elapsed time for read and write, size in megabyte, operation count fields for each task. Not only workload, but also elapsed time is printed together. It's very useful to analyze delay caused by I/O system widely. The cached I/O is excluded in those stats because this is about actual block operation. So some operations using page caches are not measurable. Not measurable. Yeah. Next, report information in I/O tracing is about device workload by size. In the red box on the picture, it shows the workload of each device for the read operation of all tasks and the proportion about subsequential operation. Most read operations consist of 4K workload. In the blue box on the picture, about 57% of operations were sequential. In other words, about 43% of operations were random I/O. This information is useful when optimizing device workload, including kernel read or head. Of course, not only total workload, but also per task workload is also shown at the bottom of the picture. Next, the report information in I/O tracing is about file workload. In the red box on the picture, it shows the workload of each file for the write operation of all tasks. Most write operations, about 100 megabytes, are performed into the test file. Actually, it's all about the guider thread using IO test command. This information is useful when tracing or analyzing task workload or file workload. Yeah, it's very nice. Next, the report information in IO tracing is about file operations. As shown in the picture, all read file operations are displayed, including time, task, offset, size, and path. The total file size is also appended into the end of the path in each line. It's detailed information, but analyzing is a little bit difficult. So let me show demo finally. PIP, PIP installing and guide helping and some tracing features and visualization features. Let's see. First of all, let's install guider using PIP. Then check version. And check commands using help command. Yeah, there are many commands supported. If you use H option with any command, options and examples for each command will be shown like this. Okay. And next, let's execute the yes program. Yeah, it just print input string repeatedly like this. Yeah, then execute it in background with redirection. And let's monitor system resources with top command. Yeah, guider top. Okay. Yes, process is using CPU merge and it's running on this core now. There are many other states as shown. Yeah. Next, let's profile system and tasks for 10 seconds. using this command. And open the output file. Yeah, then there is system information on the top of the file. And system resource usage in each interval for 10 seconds. CPU usages are whole system and specific processes, including yes, is shown. Yeah. Yeah. In addition, virtual memory, physical memory, memory details are also shown. This is about detailed stats for each interval. Yeah, this one. Okay, next, let's monitor syscalls with course text. Only write syscalls are being used. And this is the user level course tag calling the write syscalls. Next, let's monitor functions using CPU by sampling techniques. Yeah, it looks similar to previous syscall course tag. Next, let's trace syscalls with arguments and course text. This is write syscalls and its arguments, return value, are elapsed time. Next, let's trace functions with arguments and course text. Like this. And read the memory value pointed by first argument for the write function using this command. The call command ldmap is used. This is the address. Yeah. And the value is shown like this. Next feature is visualization. This is performance graph showing system resource usage about CPU, memory, I/O. This part shows CPU usage for whole system and processes. This is about total CPU and CPU usage for other processes. These labels for each graph, CPU graphs. This part is about I/O, but there is no graph because profiling options were not enough. And this part is about memory usage for whole system. Okay. Next one is timeline chart showing scheduling time slices for all tasks. Each number shown on the left is the CPU core number, and time slices of running tasks in each core are also shown. This. If you move the mouse pointer over specific time slice, information about task, event, and time is printed. Some time slices are here. You can this is arrow graphs, but I cannot catch it. 네, impossible. Last one is frame graph for course text. If you click a specific function box, zoom in is performed. And searching is also supported with regular expression. So far, I have explained some kind of useful features, including tracing of guider. There are more useful features besides the ones I described, but I couldn't explain all of them because of time limitation. For specific details, please refer to the README file in guider repository. If you have any questions, please contact me using email or GitHub. Thank you for your listening. Yeah, thank you.